Hello, I started this paper review. The title of the paper is Trajectory Design for Overlay UAV2 Communications by Deep Reinforcement Learning. UAV here refer to drones as unmanned aerial vehicles. I have always been interested in drones, so I choose this topic. In order to summarize the paper, the paper considers the cellular internet of UAV, where the sensor data can be transmitted to the mobile devices directly by overlaying UAV to device communications, or through the base station by cellular communications. Since the transmission mode of UAV may influence their trajectories, we study the trajectory design problem for UAV aiming to maximize the total utilized in consideration of their transmission mode. This problem is a Markov decision problem (MDP) with a large stage to action space, and thus we propose a multi-UAV trajectory design algorithm using multi-agent deep reinforcement learning (DRL) to solve this problem. This paper and presentation contain many applications. The means of the application is written on the right side of this slide. From the next page, the meaning of the application is written at the bottom of the page. So, I hope it will be helpful for your understanding. Unmanned aerial vehicle UAVs are regarded as promising facility to provide sensing service. UAVs transmit their sensing data to terrestrial mobile service over the unlicensed spectrum. However, due to the opportunistic channel access at the media access control MAC layer, the interface from the surrounding terminals is uncontrollable. As a solution, territorial cellular networks can be utilized to support the UAV sensing service. This paper aims to maximize the total utilization of UAVs by designing the trajectory in consideration of the transmission mode. We first design a sense and send protocol to enable the joint sense and transmission. UAV trajectory design problem can be regarded as Markov decision problem. This paper considers UTD communications, overlaying cellular network, and design UAV's trajectories in this paper. The second chapter is a system model. This section describes the model for UTD communications overlaying cellular network. And then UAV sensing and transmission models are elaborated on, respectively. This best consider on autonomic frequency division multi-access cellular network with a single base station. Look at the figure 1. Each UAV is required to sensing in task and transmit the sensory data to the corresponding mobile device on the ground. There are two modes to support the data transmissions. The first one is UTD mode. The second is cellular mode. UTD mode, the UAV transmits the sensory data to the mobile device directly. Cellular mode, the UAV sending the sensory data to the base station, and the base station transmits the received data to the mobile service. The second is UAV sensing. We utilize the probabilistic sensing model in elevate UAV sensing quality. The third is UAV transmission. There are two modes. The first mode is UTD mode. For UAV in the UTD mode, the sensory data is sent on air to ground channels, which can be evaluated by the channel mode. Cellular mode, when UAV select cellular mode, the sensory data is transmitted on air to ground channel in the first phase, and then on terrestrial channels in the second phase. In this section, we must design a sense and send protocol to coordinate multiple UAVs performing sense tasks. Then the sub-channel allocation mechanism is presented. First is sense and send cycle. The UAV performs sensing tasks in the synchronized alternative manner, which is characterized by cycles. In each cycle, UAV first sense their task and then transmit sensor data to their mobile device. In Figure 2, we illustrate a cycle of protocol which contains the S-frame. Each cycle is divided into the sensing part with the S-frame and transmission part with TU frames. In sensing part, each UAV should sense in task continuously for TS frame to ensure the sensing quality. In transmission part, each UAV attempts to send the sensor data if the base station allocated a sub-channel to it. The UAV with allocated sub-channel attempts to transmit its sensor data in the transmission mode, which satisfies the QoS requirement. The base station broadcasts all UAV's locations to each UAV. By this means, which UAV can obtain the locations of the UAVs and then decide each trajectory in the next cycle. Next is sub-channel allocation mechanism. In each frames, the base station schedules key sub-channels to maximize the sum of STP of all UAV. Since sub-channels are allocated based on STP, each UAV has to intensively complete with other by maximize its STP with each trajectory and transmission mode. Next chapter is a protocol analysis. In this section, we analyze the sense and send protocol using nested by level Markov chains. First one is auto Markov chain for UAV sensing. The sense part in the protocol can be evaluated by auto Markov chain, where state transition take place in each cycle. Look at the picture 3. UAV has two sensing states in this cycle, HF and HS, which denote that sensing is failed and successful respectively. Since the location of the UAV is changing slightly during each frame, we assume that the location of each UAV is fixed within each frame. After sensing the task, a UAV may have 3 possible situations in the transmission. one transmission failed to UTD transmission success. 3 cellular transmission success. Next is inner Markov chain for UAV transmission. This paper introduces an inner Markov chain to formulate the transmission path in the protocol. Since the observing probabilities are difficult to be deviated, we adopt a recursive algorithm to obtain the numerical result. Chapter 5 is trajectory design using DRL. In this chapter, we investigate on the trajectory design problem for UAV using DRL. Then, HTQN-based multi-UAV trajectory design algorithm is proposed to solve this problem. The first one is problem formulation. Since UAV sense and transmission have already been formulated as a state transitions in outer and inner Markov chains, each UAV can design this trajectory considering each sensing and transmission state simultaneously. In this paper, we define the utility of UAV as the total number of valid data transmissions, and each UAV aims to maximize its utility by designing each trajectory. But the utilities of each UAV is determined by all UAV trajectory. Problem 7 is difficult to solve. This problem is on Markov deep learning. We can analyze it using reinforcement learning. Therefore, problem 7 is equivalent to maximizing the total expected discounted reward of all UAV by optimizing their policies. In this chapter, we propose DQN-based multi-UAV trajectory design algorithm to optimize all UAV policies. The proposed algorithm is presented in algorithm 1, so please refer to the table on right of the algorithm. Next chapter we present the simulation result on the UAV trajectory design problem. There are two pictures. In this figure 6, we compare our proposed multi-agent algorithm with the single-agent algorithm in which each UAV updates policy considering out UAV as environment. We can observe that our proposed algorithm achieves a higher utility than single-agent algorithm. Picture 7 shows the transmission state distribution of UAV hovering over the sensing task with altitude 100 meters. We can find out that the transmission is most likely to succeed in the UTD mode when the mobile device is close to the sensing task. Look at the two pictures. Finally, we approach the conclusion in this paper. We have investigated on the UAV trajectory design problem in UTD communications overlaying cellular network. We have designed a sense and send protocol to scale the UAV sense and transmission, and analyzed using nested by level Markov chain. Simulation results have shown that our proposed algorithm outperforms the single-agent Q-learning method. We have also concluded that UAV tend to select the utility mode when their mobile device and sensing task are close to each other, and put the cellular mode and when the sensing tasks are near the base station, while the mobile devices are located at the cell edge.